first for the invitation, and second for all the efforts in putting up together this conference. So my talk will be a discussion on dimers and Orientifolds, and this is work done in collaboration with Sebastian Franco from Princeton, Ami Hanani from Perimeter, Daniel Krefel from Munich, Jaimo Park from Korea, and David Berg from MIT, that will appear presumably this week. So let me start with the motivation. The work I will be describing is some exploration of systems of D-branes at singularities, in particular about Orientifolds of such systems. There are many reasons to be interested in branes at singularities. First, they lead naturally to chiral gauge theories, so they are natural setup for model building, as was explored in old and more recent times. Second, more formally, they have interesting strong dynamics effects, for instance, confinement, or supersymmetry breaking with runaway or with metastable vacua, as explored by different peoples, and in close relation with this setup, they provide a very nice generalizations of the gauge gravity correspondence as explored by Klebanov and Strasser and many other people after them. And finally, they are nice local models of Calabi-Yau compactifications. In this line, it's a natural extension of this kind of system to introduce Orientifold quotients. It's a natural generalizations of these families of theories, and one could expect that there are similar applications for these Orientifolded systems. Unfortunately, the present techniques to study such Orientifolds of systems of D-branes at non-orbifold singularities are very rudimentary. These present techniques are based on doing orbifolding or using CFT techniques, doing partial resolution, using T-duality to other systems of branes which may be more familiar. All these techniques are really very painful to obtain results for even the simplest singularities. So there is a clear need for new tools to systematically construct and classify Orientifolds of systems of D-branes at singularities. So this kind of situation is not new. In fact, there was a similar problem for theories without Orientifold actions, just D3 branes sitting at different Calabi-Yau singularities, where all the techniques were rudimentary and very painful, but this problem is now solved in terms of the so-called dimer diagrams, which naturally encode all the information about the gauge theories on the branes and the geometry at which the branes are sitting. And these kind of tools apply to any toric singularity, which is not the generic case, but in any way it's a huge set of examples. So these dimer diagrams essentially correspond to periodic tilings of the plane, which have the property of being bipartite. Bipartite means that there are nodes in this kind of graphs that tile the plane, and the nodes can be colored black and white in such a way that the edges always join nodes of a different color. So one draws this kind of picture, which corresponds to a tiling of the plane, which is periodic. So there is some kind of unit cell, and you can think about it as a tiling of the torus. And one can read out the information of the gauge theory from this picture by interpreting each phase of the tiling as a gauge group, a gauge factor in your gauge theory. The matter multiplets are associated to edges that correspond to bifundamental representations of the two gauge factors corresponding to the phases separated by a given edge. And finally, the nodes of the picture of the graph correspond to superpotential couplings between all the edges that enter into the edge. And there is the color coding of black and white means that there are certain signs in the complete superpotential of this theory. So out of this you can reconstruct the quiver theory, which is probably familiar to all of you, where each dot corresponds to a gauge factor, in here it would be a phase, and the different arrows correspond to matter multiplets, which in here correspond to the edges. But in addition to just this picture, you have the information about the superpotential built in your picture. There are also very nice tools developed by these people to read out the information about the geometry at which the branes are sitting by drawing certain paths, the so-called zigzag paths, in this picture, which give you essentially the toric data of the singularity at which the branes are sitting. This kind of tools has proven extremely insightful to study the gauge theories of the branes at toric singularities, and also to study the gravity duals. A lot of the information about these gravity duals is encoded into these pictures. So one expects that they also encode a lot of information about the possible Orientifold quotients that one can impose on this kind of system. Since Orientifolds are just quotients by a symmetry of the system, it's natural to think about these symmetries as symmetries of the dimer diagram, in the sense that the dimer diagram encodes all the information about the gauge theory. So just thinking about this kind of symmetries, one can immediately realize that there are two kinds of Orientifolds one can impose on the dimer. They correspond to symmetries with fixed points on the dimer diagram, that is, reflections with respect to a point, but because of the periodicity, there are 4 fixed points in the unit cell, or reflections with fixed lines on the dimer, and because of the periodicity, there are typically 2 lines in the unit cell. Okay. In this setup, for a given geometry, that is for a given dimer diagram, different Orientifold models will correspond to different choices of signs for these Orientifold points or Orientifold lines, as we will describe in what follows. So let me just focus on the first class of Orientifolds that one can do, which corresponds to Orientifolds with fixed points. Essentially what we did is we devised a set of rules that encode all the combinatorics about these models, which are consistent with all known examples of Orientifolds of toric singularities that appeared in the literature, and which are consistent with partial resolution. So you can think about these rules as a proof, or you can think about these rules as some kind of induction where you start proposing the rules for the simplest singularities, and then you impose that this is consistent with partial resolution, or the inverse process, so that you derive the rules for more complicated singularities. And the rules are essentially that you have these 4 fixed points. You can think about these fixed points are Orientifold planes in your configuration if you give a physical implementation of this setup, and then what you can do is assign charges to these Orientifold points, which essentially control the kind of Orientifold projection that this is imposing. For instance, if you have some Orientifold plus or Orientifold minus on top of a face, that means that this gauge factor is mapped to itself under the Orientifold action, and then it can be projected down to SO or SP, SO for the plus sign and SP for the minus in our conventions. Similarly, if you have some O plus or O minus on top of some edge, this corresponds to some bifundamental which is mapped to itself, so it projects down to a symmetric or two-index symmetric or two-index antisymmetric representation, corresponding respectively to O plus or O minus. Finally, let's say empirically, we realize that there is a constraint on the total number of signs that you can assign here, which is related to supersymmetry, and the rule is that the product of the charges of the Orientifold planes in here should be -1 to the k in a dimer with 2k nodes. So just to give one concrete example, consider just the simplest situation, which is D-branes in flat space or in C3. This has the dimer has 2 nodes. This means that the product of the charges of the Orientifold planes must be minus, so you have a number of possibilities, that is possible Orientifolds of D-branes in flat space. For instance, choosing here for the Orientifolds A, B, C, D, plus, minus, 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 the gauge theory that you obtain is SON with 3 two-index antisymmetric representations. This is just the n=4 preserving Orientifold of the system of D3 branes in flat space, corresponding to imposing some Orientifold 3, or locating some Orientifold 3 on top of the D3 branes. Similarly, other choices like plus, 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 minus give you a projection which gives you SON with 2 symmetrics and 1 antisymmetric, and you can realize that this corresponds to putting some Orientifold 7 on top of this. Other choices which do not respect this rule, like plus, 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 will give you SON with 3 symmetrics, and there is no supersymmetric Orientifold that does that. So in a sense, this is in the simplest example, you know what the answer should be, and then you cook up some rules that do the job, and then you make the rules consistent with partial resolution, which corresponds to these rules in here, so that you can generalize to any toric singularity. And in fact, it's very easy to construct any model that you want. Let me just present some examples. This is just the dimer diagram of the set 3 orbifold singularity. You have the 4 fixed points, and then you have different choices. For instance, this one will correspond to a theory with gauge group SON times UM, and this matter content, and this is a well-known Orientifold constructed by Antel, John, Pardisi, Bianchi, Sagnotti, and Stade in the prehistory of open string models. You can construct many other models which are not in the literature but are easy to construct because this is an orbifold theory. You can use CFT tools to verify, let's say, the rules that we have devised, and obtain other models that nobody cared to construct if you wish. But you can take these rules and apply them very easily to models which are not orbifolds and are very difficult to treat with other tools. For instance, it is straightforward to construct Orientifolds of the conifold. You just take the dimer, which corresponds to this set of squares. This is the unit cell. You have your 4 fixed points, and then you assign signs in here consistently with the rule of signs, and obtain Orientifolds with group UN, and then a distribution of 2 index symmetric and antisymmetric representations. In this simple example of the conifold, there are other tools that you can use to verify that these results are correct, And then once you are sure that these rules are correct, you can apply them to a long list of known and new Orientifold models. Once that you know how to classify different possible Orientifold gauge theories associated to a given dimer diagram, what you'd like to know is what is the precise geometric action that you're doing to obtain this gauge theory on the branes. So what you need out of our rules is a way to characterize what is the precise Orientifold action, omega times r times minus 1 to the FL, that you are modding out by, where omega being worldsheet parity and r being some involution of your geometry. So the simplest or the best way that we found to do that is to regard the geometry in the space transverse to the singularity as the moduli space of the gauge theory, and in particular to regard the gauge invariant mesonic operators of your gauge theory before Orientifolding, the parent theory if you wish, as coordinates in your parent geometry on your covering space. So these gauge invariant mesonic operators are very natural objects in your dimer theory. They simply correspond to closed paths on the dimer, essentially because what you do is you take different bifundamentals coming and going out of different phases and contracting them with a trace. So they correspond to closed paths like this one. It starts in one, you take this bifundamental, you multiply by this one, and then you trace this result, which is a closed loop. So essentially what we did is, we obtained a set of rules that allow you to read out what is the Orientifold action on the mesons constructed in the dimer, and essentially this is telling you how the Orientifold is acting on the coordinates of your geometry, that is on your geometry. So essentially for each meson like this one, which is passing through the Orientifold points, essentially it picks up a minus sign every time it crosses some Orientifold minus sign. Okay, that takes care of this kind of mesonic operators. If you have mesonic operators like this one, which surround a set of nodes, it corresponds to some homologically trivial path, and this one pick a minus sign per node enclosed by the path. And finally, there may be paths which are not passing directly through the Orientifold, but rather are mapped to some other image mesonic path. And essentially for these ones, what happens is that they pick a minus sign per node and per Orientifold minus in the strip which is in the middle, defined by these two different paths. And again, all these rules define geometric actions which are consistent with all known examples, but they generalize to any arbitrary toric singularity. Let me go to the second class, or more briefly to the second class of possible Orientifolds that one can do, which correspond to Orientifolds with fixed lines. Again, what we did is devise a set of rules which are consistent with all known examples in the literature and with partial resolution. So by induction, you are sure that they work for any toric singularity. The basic idea is to consider the Orientifold lines and to assign charges to them, but one should be careful of doing that in a way consistent with the unit cell structure. What I mean is that Orientifolds with fixed lines or fixed line symmetries exist only for tori with unit cells which are of this form, let's say rectangular or tilted in this fashion. Essentially in this case the two fixed lines are independent. You can choose the two signs independently, but in this case the two lines are in fact the same, so there is only one sign that you have to choose. So one should be careful with that to obtain consistent models. And once you have made this assignment of signs, you again have the same kind of projections, or plus or minus project down SO and SP if you have a gauge factor on top of the Orientifold line, and the O plus or minus on top of some edge project down to symmetric and antisymmetric representations. And in this case, again, for technical or empirical reasons, there is no constraint on the Orientifold line charges. They can be chosen independently. There is no rule associated to supersymmetry. So just to give one concrete example, let's consider the D3 branes at the C3 and flat space, and just the possible Orientifolds, which corresponds to these fixed lines examples that one can do. So let's consider, for instance, this line reflection symmetry. This is the unit cell, and one can see that these two lines actually correspond to the same. So we are in this kind of situation. There is only one sign to choose. For instance, choosing the plus, the theory that you obtain with these rules is SON with two symmetrics and one antisymmetric, and then you see that this corresponds to some Orientifold 7 plane, which you can understand by other tools. So again, one can generalize this to many other examples, and again, I will not describe it, but one can construct a similar set of rules to obtain what is the geometric action that one is modding out by. So just to provide some concrete example, one can do Orientifolds of these complicated orbifold singularities for even or odd order of the orbifold group. This corresponds to the even case where the two lines are independent. This corresponds to the odd case where the two lines are the same. And then you can construct two possible kinds of Orientifold planes in here, which corresponds to having different signs or having the same sign. and in here you have only one possible sign, and all the classification agrees with things that you could construct with other tools, with the advantage that this rule generalizes to any toric singularity, even if you don't have any other tools to start. So one can construct a long list of known and new Orientifold models using these tools. In order to provide some understanding of these rules, what one can try to do is, for instance, to go to the mirror picture, because the diagram, as realized by these people, is geometrized in a sense in the mirror geometry. The mirror geometry, even in the absence of Orientifold planes or whatever, corresponds to a fibration over a complex plane of a Riemann surface sigma times a C star fibration with certain generations that tell you what is the compact, the set of compact 3 cycles, the compact homology supported by your local geometry. In this kind of situation, the mirror of D6 branes corresponds to the mirror of the D3 branes corresponds to D6 branes wrapped on a special Lagrangian 3 cycles, because this construction is supersymmetric, and all the relevant dynamics of these branes is encoded in the 1 cycles wrapped by these special Lagrangian cycles on the Riemann surface. Everything is encoded on the Riemann surface. For instance, the intersection number of the 3 cycles corresponds to simply the intersection numbers of the 1 cycles on this Riemann surface, and they tell you essentially how many bifundamental multiplets you have. And similarly, these instantons, which are fully supported on this Riemann surface, tell you what are the superpotential couplings via wall-sheet instantons in this kind of theories. So in this kind of setup, you can try to understand what Orientifolding means, and essentially, because this is the only supersymmetric choice, it should correspond to modding out by some anti-holomorphic involution that defines some Orientifold 6 planes in your configuration. And again, one expects that the only relevant part of the Orientifold of the 3 cycle wrapped by the Orientifold 6 plane will be the 1 cycle that corresponds to the projection on this Riemann surface. So this is just one concrete example that corresponds to the so-called suspended pinch point singularity. This is just a picture of the Riemann surface. These different cycles corresponds to the different D6 branes, and this plane here corresponds to the anti-holomorphic involution by which one is modding out. So this is perhaps a more clear picture, and one can see that the different branes are mapped to each other or left invariant, etc., etc., following the set of rules that we have proposed. So one gets a geometric understanding of the rules we had before. And one important ingredient is that, roughly speaking, morally speaking, a crucial point is that the Orientifold planes that correspond to the intersection of this plane with the Riemann surface contain several branches, because this Riemann surface has punctures going to infinity. So these different branches correspond in fact to different and independent Orientifold planes, and you do have the freedom of choosing the signs of these Orientifold 6 branches. This is the origin of the choices of signs that we had in the dimer picture, only that it was very easy to systematize in that language. Very good. Let me now turn in the last, 6 minutes to different applications of this kind of system. There are certain situations where having Orientifold planes can play a crucial role in the physics of the system. I mean, you can have phenomena that do not take place in the absence of Orientifold planes, and we expect that the kind of rules that we are deriving and the kind of models we are constructing may allow you to have a more systematic study of these models. For instance, something which is a nice application of having Orientifold models is to getting gauge theories with supersymmetry breaking, and a hint that this Orientifolding may be the right idea comes already from '98 in this system study introduced by Lykken, Poppitz and Trivedi, which corresponds to D3 branes at some Orientifold of the set 3 orbifold, which has this field content plus some superpotential, which already showed supersymmetry breaking, but unfortunately with runaway to infinity along some baryonic direction. So you may expect that nevertheless there may be other models which break supersymmetry dynamically. And in fact, it's very easy to construct theories which reproduce SU5 gauge group with just one family, 10 plus 5 bar, and no superpotential. And this theory is known to have, is expected to have a dynamical supersymmetry breaking, as shown already in the 80s by these people. So using our rules, it's very easy to show or construct several examples based on, let's say, the set 6 orbifold or the so-called pseudo-del Pezzo's singularities, where choosing different Orientifold locations with different signs, one reproduces this theory. Just to give you this example, imagine that you locate no ranks in here, so you put 0 rank on these branes, and then you locate 5 D-branes, let's say for this phase here, and 1 in here, and the 5 in these phases here. You will have some O1 times U5 gauge theory with one antisymmetric representation, and in here 1 by fundamental of SO1 times U5, which is nothing but a fundamental of U5. So exactly this theory, and no superpotential coupling between this field, let's say, and this field. So this is a simple way of realizing this theory. which shows that one can realize dynamical Susy breaking with a stable vacuum breaking supersymmetry in a string theory in this particular setup where you have the coupled gravity, if you wish. So it's very simple to construct these models and to generalize them to other singularities. I mean, one can draw this with just a few strokes of a pencil. Let me just point out that there have been previous discussions of realizing this gauge theory by imposing Orientifolds by different people, but essentially they were obtaining them by Orientifolding the quivers of the gauge theory, and it may be, well, just Orientifolding quivers may be a tricky thing because you miss all these detailed correlations of what are the different Orientifold projections in the different regions of your theory, let's say. So one should be careful with Orientifolding quivers, and we think that this approach of Orientifolding dimers really contains all the key ingredients in a very simple way. So let me turn to the second application, which corresponds to thinking about D-brane instantons in this kind of local models of D-brane singularities. So we'll be discussing the coming talks this afternoon. It has been realized that one can generate interesting four-dimensional gauge theory operators from D-brane instantons that correspond to string instantons, not just gauge theory instantons. And the key point is that whenever you have some D-brane instanton which intersects, in a sense, non-trivially, the D-branes that lead to the four-dimensional gauge factors, there are fermion zero modes of the instanton charged under the four-dimensional gauge group, which must be saturated by insertions of four-dimensional operators of the gauge theory. And there are different papers discussing how to do that in precise detail. So something important is that if you're interested in generating a superpotential term, what you require, or you should require, is that there should be exactly two fermion zero modes uncharged with respect to the gauge group. And essentially, if you don't have Orientifolds into the game and are just working in perturbative type 2 theory, it's easy to see that there is some enhanced n=2 supersymmetry on the back of your instanton, which leads naturally to 4 Golstinos associated to the 4 broken supersymmetries by your BPS instanton, which means that you have more than these two required uncharged fermion zero modes. Now, if you do Orientifolding, the Orientifold projection can remove 2 of these 4 zero modes and leave you precisely the adequate quantity to really generate a superpotential. So this has been exploited or discussed by different people in different contexts, and in particular it can be applied to systems of D-brane singularities. That is, you can consider a system of D-brane singularities and think about what are the possible instanton effects that could generate this kind of operators. To really generate superpotential terms, you need Orientifolds to remove the extra n=2 accidental zero modes, and it's very easy to construct examples where this is realized. For instance, this dimer here corresponds to the set 3 singularity, and this is just some particular Orientifold, and putting some gauge factors, some branes here, giving you some 4-dimensional gauge theory, and some instanton brane on this face, one can see that this instanton has the appropriate fermion zero mode structure to generate a non-trivial operator for this gauge theory. And this is just reproducing one example constructed by Arburio, Bertolini, etc. One can construct other examples. This is a more complicated one in the sense that it corresponds to some Orientifold of an orbifold of the conifold, so it's really a tricky thing, but it's trivial to do in terms of these dimer diagrams, and this corresponds to another model constructed by Arburio and collaborators. So this is another potential application, another situation where Orientifolds are crucial, and we expect our tools to be useful. So now, without further ado, let me turn to conclusions. In this talk we provided, or we described tools how to classify Orientifolds of toric singularities. We can very easily reproduce all known Orientifolds, and very easily many more, in fact infinite families, and we devise rules which are consistent with partial resolution so that we are sure that they work in general. We described several interesting applications, in particular to dynamical Susy breaking in a particular example. It would be interesting to find other examples, and to D-brane instantons, again reproducing examples in the literature, but one can very easily construct other examples. And let me finally point out some open directions. One would be, as I was mentioning at the beginning, that was my original motivation, to carry out a systematic study of the new families of theories, because one expects that these theories in general will have a rich set of infrared dynamics with confinement, Susy breaking, and many other patterns that it would be interesting to explore in detail. And finally, also it would be nice to improve the understanding of the mirror side and really derive these rules, if you wish, from first principles. Thanks a lot.
Questions? Yeah, as one of your interesting examples, you mentioned this theory SU5 with a single 10 plus 5 bar, and that and I guess a wider class of gauge theories were argued in the 80s to break supersymmetry, but they were called non-calculable because the vacuum is very hard to study. So there's no weak coupling expansion. If you have a geometric description of these, does the geometry give you any new tool, maybe by a geometric transition, to actually study the low energy dynamics?
Not yet. I hope that there is some stringy way of understanding why these theories break supersymmetry in some minimum, but we have not reached this understanding yet. So for the moment we are classifying these things and then finding some concrete examples of phenomena, but we're not exploring systematically. So this would be on this part here. That's for the future.
More questions? Are there any more questions? If not, let's thank our speaker once more. Our next speaker is Dr. Blumenhagen from Munich. His title is D-brane instantons in super